Hello students, this is Professor Chalai, and in this video we're going to go over some of the things that you may need to know for our upcoming molecular spectroscopy lab. Let's get started. So in this lab, our entire aim is to find the concentration of an unknown solution of FeSCN2+. This solution has a very sort of deep red color. And so because of that, we're going to use Beer's law and absorption to figure out the concentration. Now, if we remember, Beer's law says that the absorption is related to some constant E times some constant B, that's usually path length, times the concentration of the solution. So if we know the absorption and we know what these different values are, we can find the concentration of the solution. We are very familiar with Beer's law from our earlier lab, but if not, you can ask your instructor for more details. Now, here's the thing. We can easily find the absorbance of a sample, right? We just put it in our little spectrometer that we've used before. But we need to figure out what these constants are before we can go ahead and find the concentration of the solution. And we've done this before by plotting a graph, right, of absorption on one axis and the concentration in molarity on the other axis. And so we'll get a bunch of samples and we'll plot a graph, right? We know that the equation on first straight line is y is equal to mx plus b. There we go. Now in this case, y is just the absorbance, m is the slope, so let's leave that as m, and x in this case is big M, molarity, plus some constant b. So if we compare this to our Beer's law equation, right, this is Beer's law, we can easily recognize that m should in fact be this E times B constant that we need to find. So by using this equation, if we plug in for the absorbance, we know the slope, we can find the concentration. Now you might be wondering, what is this B over here then supposed to be? Well, if you calibrate your instrument properly, B should be very close to 0 for this lab. If B is not close to 0, it means that you forgot to calibrate your instrument, which is always a very important first step. Okay, so this is the sort of final product of this lab. We're trying to find a concentration of some unknown solution of this guy using Beer's law by plotting some data points and using the equation of best fit. However, how are we getting these data points? What we need to get these data points is a bunch of solutions of this guy where we exactly know what their concentrations are, and then we'll need to find their absorption. So how do we go about doing that? Well, we can create that ion using this reaction. Iron 3 plus SCN minus reacts together to form this compound. Iron 3 plus solution comes from iron nitrate, which is a pale red solution. This SCN is going to be colorless. And then when they react to form the product, right, this is going to be a very deep red. This is the deep red ion that we're looking for. So we can create solutions where we know exactly the concentration so that we can create this curve right here before we can go ahead and find the absorbance and concentration of the unknown solution. Okay, so to do that, we're going to create a bunch of what we would call standard solutions of our product by reacting known concentrations and volumes of our reactants with some water to produce our product with a known concentration. And so these are the values you're going to use. So what you need to do then is to figure out which one of these two reactants are limiting reactants for every step. And therefore that will tell you how much product you'll have, and therefore how much what the concentration of the product is, which is what you need to know before you can find the absorbance, right? You'll know exactly what the concentration of these ions are. Okay, so I'm sure you're all very familiar with limiting reagent calculations, and if you are, you can just skip ahead of this part. But let's, the question up here asks you to kind of calculate a sample concentration calculation using the first row. I am not going to do your calculations for you, so I'm going to make up some additional numbers that are not on this table, and I'll do those as examples. So let's say instead you had, I don't know, 2 mils over here, I don't know, 1.5 mils over here, and you added 25 mils of water to the whole setup, right? If I were to perform this calculation, what is the moles of product obtained, right? Considering the limiting reagent, and therefore what is the concentration that I obtained? Well, let's see. In a limiting reagent calculation, the limiting reagent is the one that gets used up first, or you can think of it as the one that produces the smaller amount of product. So we need to try both of our starting product to see which one would produce, both of our starting reactants to see which one would produce the smaller amount of product. Let's do that. Okay, so let's figure out how much of our product that we are interested in comes from, let's use the first one, this KCN, KSCN, or SCN minus is the ion that we're really interested in. So in this example that I'm setting up for you, we're starting with 2 mils, and the concentration that we're starting with is 0.00200 molars. So let's set that up. So we're starting with 2.00 mils before we can of SCN minus. Now before we can find a number of moles, since big M, molarity here is moles over liters, we need to convert this to liters. We know that 1,000 milliliter is 1 liter, so that will convert it to liters nicely. All right, to find the number of moles, we just use the concentration here, 0.00200, so 0.00200. We know this is moles over liters, right? That's what big M is, so liters cancel out. But this will give us moles of SCN minus, but we want moles of product. And let's look at the balance equation. The mole ratio here is 1 to 1 to 1. So that makes it easy, right? We know that 1 mole of SCN minus gives us 1 mole of our product, which is FeSCN2+. So if we plug these into our calculator, I believe we should get 4.00 by 10 to the minus 6 moles of FeSCN2+. Okay, that's for the first reactant. What about the second reactant? Let's use a different color for the second reactant. And so here we need to figure out how much product, FeSCN2+, we get from the other reactant, which is iron 3+, iron 3. Here we do the same calculation, right? We start with 1.50 mil and we have 0.200 molar concentration. So 1.50 milliliters of Fe3+, we convert first to liters, and then we multiply by the concentration. And this will give us moles of Fe3+. But we want moles of products, so we use the mole ratio. Again, it was just 1 to 1. So 1 mole of Fe3+ gives us 1 mole of our product. There we go, so that cancels there. And so if we run all of this in a calculator, I believe we get something like 3.00 by 10 to the negative 4 moles of product. All right, so which one produces the smaller amount of product? Well, this here is a smaller amount of product, which means SCN here is our limiting reagent, which means this is the moles of product we will form. So in this table here, I will just enter 4.00 by 10 to the negative 6 moles. And now for concentration, let's create some space. We know concentrations is moles over liters, right? So let's use concentration of the product. So concentration is moles, which we know what it is. We just calculate that. 4.00 by 10 to the negative 6 moles divided by the volume. The total volume comes from the reactants that we added, right? 2 mils of the first reactant, 2 mils of the 1.5 mils of the second reactant, and the water, right? Because it's the concentration of the whole solution. So let's add them all up. What do we have? 2.00 mils plus 1.50 mil plus 25 mils of water. Right, this all, if I this all will give us, let's see, 25 plus 2 is 27, 28.50 milliliters. But we actually need to convert this into liters, right? And we do that by dividing by 1,000. 1,000 milliliter is 1 liter. So if we sort of divide by all of this, I know it's sort of set up a little bit weirdly because I'm running out of space. It's 4.00 by 10 to the minus 6, right? That's right here. Divided by the volume in liters should give us a number of around 1.40 by 10 to the negative 4 molarity. And so this is a concentration of our final product. So I'll write that 1.40 by 10 to the negative 4 molars. And then after you've calculated all of the concentrations and made up all of your solutions, where you'll have your beaker or flask, you'll add the first reactant and the second reactant and water, and you'll observe your product that is deep red that we talked about. Maybe this is a better deep red, right? You know exactly what the concentration of that solution is, so you'll just take a little bit of it, put it in your cuvette, right? Put it in your spectrometer and figure out what the absorption was. And now you'll see some crazy absorption, but the highest peak should be at what we call, so this is wavelength, right? And this is absorption. The highest peak should occur at what we call the lambda max, which for this experiment was 455 nanometers. So you'll take the absorption at that point, and that's what you'll record here. So once you have all of the data in this table, right, you can go ahead and plot your graph of absorption on the y-axis versus concentration of the x-axis using Excel that we've done quite a bit of time now. All right, I think that's all all that we would need to know for this lab. If you have any other questions, please ask your instructors. It's a very fun lab. We get to see an awesome color change when this reaction happens. And not only do we see this color change with our naked eyes, but we get to monitor it with a spectrometer as well. So that should be really fun. All right, have fun in labs. And if you have questions, please let your instructor know.